next, I'm hoping that we have Pablo there. Pablo Hermosin Herrera, are you there?
Yes, can you hear me?
Fantastic. I'm going to throw directly to you to save some time. Thank you. Over to you, Pablo.
Okay, let me check if the clicker app is working. Okay, great. So thank you very much for the introduction. So in this talk, I'm going to talk about the work we've been performing here in Deimos Space in Spain with our colleagues in Asteroid Corporation in the US regarding the optimization to thousands of trajectories to different near-Earth asteroids that are very close to Earth, actually. So if we move to the next slide, this is a recurring topic, a recurring slide that you have been seeing the last days, probably a lot, but it's necessary to, let's say, to present the problem, and it's the asteroid mining problem. Why should we mine an asteroid? So, as you've been seeing in the last days, and you can see here, asteroids are full of materials that can be of very good use here on Earth. So, we can say, for example, water, minerals, metals, and also other human consumables like oxygen, for example. So, taking this into account and having as reference this 50-meter class C asteroid, we can have approximately a value of the asteroid in the order or bigger than $350 billion, and yes, billions. So taking this number into account, I think that the question, why should we mine an asteroid, it's really well answered. So starting from here, I mean, we know that it's interesting to mine an asteroid, looking at this, but where are those asteroids? So we have thousands of small Neos close to Earth that, as we've seen, are a rich source of minerals and water. And since there are so many of them, we need fast and efficient methods to calculate round-trip trajectories because, as been said in the previous days, the value of the asteroid itself is there once you use the resources that it gives you. I mean, you have to go to the asteroid and be able to come back to Earth in order to make use of the value of the asteroid. So in this analysis, we have performed we have a catalog of a realistic synthetic population of more than 4,000 unknown objects. This synthetic population has been generated by our colleague Robert Jedicke in the University of Hawaii. And you see there the publication in case you want to check how he developed this. And with this unknown term in the sentence, we mean that these orbits are not known before detection. So we have to wait for these asteroids to come close enough to Earth in order to be able to track them and of course go into to them to extract their resources. So as you can imagine, this is a very big constraint in the design of the trajectories because you have to be always ready to launch. And of course, the duration of the mission, especially the outbound leg, cannot be very long because since the observations you can do during the passage of the asteroid close to Earth are not very frequent, the uncertainty in the asteroid orbit is very big. So you cannot wait too much before you go after the asteroid because you may lose track of it. So that would be worthless in terms of going on delta V analysis. So with this population, first thing we did was check how many of those asteroids are within 0.05 astronomical units of the Earth in a period of 100 years, approximately, which is considered as the maximum detection distance. And taking that into account, we have approximately that 70% of the asteroids in the catalog are reachable in between 2020 and 2090, more or less. And with a constant or more or less constant number around 80 per year. So we have a lot of missions per year to go to asteroid and extract their resources. So taking that into account, now we move to the trajectory optimization to those asteroids. So here, Transastra basically developed the full asteroid mining concept and the business case. And on our side, on Deimos side, we did the trajectory optimization, but assuming the in situ utilization of the asteroid water as propellant. So Basically, we are able to go to the asteroid using a water-based propellant system that we can carry from Earth. But then once we go to the asteroid, as you can see in the right picture, it's the Transastra picture, you see how you can encapsulate the asteroid and using the optical mining technique that they have developed to extract the water from the asteroid in order to use it to come back to Earth with it and exploit these resources. And of course, what we had to do was to characterize this water propellant system for it to be realistic in terms of ISP, thrust, and so on, and implement that in our tools in order to optimize the trajectories, taking into account the propellant system characteristics. And with that, we showed it's feasible to use this asteroid water to bring it back to Earth or to the Earth-Moon system and exploit the resources. And you see an example on the left that you see the three orbits are more or less one over the other because the asteroids are very close to Earth. But the black arrows show the intensity of the thrust during the optimization. So in the beginning, you see there is an increase of the thrust, bigger thrust, in order to get out of the asteroid, and then you have some small braking points and a bigger brake maneuver at the end in order to rendezvous with Earth. This is an inbound trajectory. So the point here is, okay, we can go to the asteroid, we can use its resources to bring it back to Earth, but how much of the asteroid is left when we come back to Earth? Because at the end of the day, we want to come back with something in order to exploit it. And this is the analysis we've been doing, assuming 100 tons asteroids, so asteroids between, I don't know, around 5-10 meters diameter. We can assume that the return mass per year could be in the order of 2,000 tons. And it's really constant between 1.5 and 2.5 thousand tons during the complete century. The decay you see in the latest years is because we have a constraint in the duration. So and we analyze up to this century. So the farther you go in the century, the less time you have to being able to fulfill all the constraints. So that's why you have less missions. But in case we did the analysis up to 2120, you will see that the number remains more or less constant. So apart from this, what's the conclusion of this analysis? The main conclusion is the fact that we have shown, and this preliminary concept is feasible to perform this round-trip mission to Neas using the water-based propulsion system. The return mass per mission is in the order of 50 tons, with some of the asteroids or the return mass over 80 tons for asteroid of 100 tons. So it's a lot of mass, but it's mass that we are using. We are basically refueling on space, so you don't have to take into account the fact that you have to carry that mass because it's already in the asteroid. And of course, there is still some work to do. We can perform more detailed analysis in order to refine and reoptimize the trajectories to being able to return more mass. There's also the possibility to do the optimization of the mission schedule to maximize the amount of water and minerals that we bring back to Earth in a given amount of time. Because sometimes it may be interesting to, even if you see an asteroid appearing, maybe interesting to wait for the next time it appears, because in the second time, the delta V of the round-trip mission is smaller. So in that case, you will be able to come back to Earth with more resources. And of course, it's also the point of the complete analysis of the GNC solution, because it can have a huge impact in the detection and the tracking of the asteroid. Because as I said in the beginning, since you don't have that many observations, the uncertainty in the ephemeris is very big. So you have a big constraint in the reaction time and the duration of the missions. If you are able to observe the asteroid from the spacecraft itself on board and correct the ephemeris live, you will be able to relax a bit those constraints and find better missions in terms of delta V, and of course, if delta V is lower, the return mass would be greater. So you will be able to exploit more resources in that case. And that's all on my side. Thanks very much. I don't know if we have time for questions, but if not, just use the platform to contact me directly if you want.
Thank you very much indeed, Pablo. There are a few questions here coming in, a number of questions. As with all of the speakers yesterday and previous days, you can jump online as well once you're out of this Zoom room and answer them. But just to pick up on one of them, from an anonymous person, the question is, can you precisely determine the composition of elements and hotspots on the asteroid without sending a scout spacecraft?
Well, I'm not an expert on the composition of asteroid. I guess, of course, this type of this percentage of materials that we can assume the asteroid have and depend on the asteroid itself, of course, so there will be a margin of error, but taking into account the observations, and you can at least categorize the asteroid in families, and with that you would have a preliminary values to determine if it's worth it or not to go to the asteroid. Of course, you may go there and the composition is not the one that you want, but at least you can have a very first guess of the type of asteroid you're going to.
Thank you very much. Patrick, there's a number of questions pouring in right now at the end of the talk. Is there anything you'd like to pick up on?
Actually, I have my own question because that will, the other questions have a consequence. So if you're targeting 50-meter size asteroids, how do you despin them to capture them? This was the same problem with the asteroid retrieval mission, because some of these bodies rotate in less than 1 minute. And moreover, their cohesion may be super low, so as long as you touch them, you may just destabilize them. So did you take that into account?
Yeah, well, maybe that's, I mean, what we're targeting are smaller asteroids in this first stage, because, I mean, this is very linked with the Transastra solution. So right now we are targeting smaller asteroids and the order of few meters. And then in that case, there's still, as I said, work to do in the GNC in order to be able to get close to the asteroid safely and match the rotation of the asteroid and so on in order to take that into account. So at this stage, it's just a preliminary concept or proof of concept, taking into account more or less or more in detail the interplanetary trajectory part. And then there's next step to do in order to being able to explain more in detail or to analyze more in detail the close proximity operations with the asteroids.
Thank you so much for your time, and I'm sure you'll jump online and answer the questions that are coming in right now. Sadly, I have to move on.